Hello friends. Today we are going to understand the concept of AC analysis of common source amplifier using MOSFET. What is mean by amplifier? We are talking about voltage amplifier. It is an electronic circuit which increases amplitude of a weak signal to a desired level without changing its frequency. Why this amplifier circuit is so important? In front-end electronics, we have sensors and transducers. These transducers and sensors detect the physical quantities. Many times we need to convert these physical quantities to electrical signal, and output of these sensors and transducers is very weak. It need to be processed further. So, before that it should be amplified. As well as in communication circuits, we have different types of amplifiers. So, in particularly voltage amplifier, the amplitude is amplified. This amplitude is weak and it need to be amplified. See this. And we have amplifier using BJT as well as we have amplifier using MOSFET. So, what is the difference? We will see the difference also, but before that, to understand the AC analysis of MOS amplifier, we should know the AC equivalent circuit, we should know the small signal model of MOSFET. I am drawing the symbol of NMOS transistor and we are going to develop the small signal model of NMOS transistor. So, it is the source, it is common to input port. So, this one is input port and it is output port. So, it is drain, gate and source. This is complete source line, it is ground point. So, what we have in the output? The interesting quantity in case of MOS transistor is drain current and it is flowing drain to source as it is at higher potential plus and minus, and we have here V naught and here we have Vi. What is Vi here? We have VGS, AC gate source voltage, and V naught we have VDS, AC drain source voltage. But how it is done? So, how it is done? What is the relation between output and input here? It is not similar to bipolar junction transistor. See here, what is the change? So, it is the transconductance GM. So, it is dou ID or dID by dVGS, small change in drain current to the small change in gate source voltage. So, it should be AC keeping VDS constant. So, simply we can write this as ID. So, it is lowercase d. So, it is ID AC drain current is equal to GM times VGS. What is GM? Transconductance, ratio of current to the voltage. Therefore, it is termed as transconductance, and this transconductance is an important figure in case of MOS transistor. Whereas, in case of BJT, we have beta in common emitter configuration, and beta AC is equal to IC upon IB, and collector current is IC is equal to, it is beta AC times IB. So, this is the important equation in case of BJT, okay, and BJT is operated in active region. See, ID is GM times VGS. So, we have meaningful relation for this. What is that? What this tells us? So, it tells us that ID is function of VGS, okay. So, VGS is what? Swing at the input. Here we have swing. So, this is the swing at the input, and again we have a change in the drain current, this one. So, it is the change in the drain current. So, drain current swing depends upon the swing in the voltage at the gate. Why it happens? Because gate current Ig approximately 0, okay. Ideally the value of Ig is 0, practically so very small amount of gate current flows, and that is the greatest advantage we have for using MOS transistor, okay. Its input impedance is very high because input junction is reverse bias. We can say it is isolated, completely it is isolated. So, swing in the gate source voltage will produce a swing in the drain current, okay. So, I am going to draw the circuit for this. So, it is small signal model for this one. By using this equation, we can represent this as, so it is the gate, say gate is here and we have VGS input quantity which is voltage and it produce a change in current at the output node. So, this one is current source GM VGS. So, this current source is controlled by this voltage and this is equal to ID and we have, so it is small R naught and we have drain here. So, this completely represents the MOS transistor. So, this represent the MOS transistor series. What is R naught? So, R naught is finite output resistance, already we have a lecture, special lecture on this, and R naught is equal to, it is lambda IDQ raised to minus 1 or it is equal to 1 by lambda IDQ. We have developed this relation. What is lambda? Lambda is channel length modulation parameter and ID is the DC current which is set at the quiescent condition. Okay. So, we are using this model to analyze the circuit diagram of common source MOSFET amplifier. Let us draw the circuit diagram for amplifier. Transistor, the center, source resistor and drain resistor. First I am going to draw and then I will label it. I have drawn circuit diagram of common source MOSFET amplifier. In the center, we have NMOS transistor here, which is biased by using R1, R2, RD and RS. Okay. So, these are the biasing resistors. How they bias resistor? How they bias transistor? Here, this is amplifier circuit and this transistor is operated in saturation region. Okay. We have developed small signal model and we understood that why it is saturated, why it is used, why it is biased in saturation region. Because in saturation region, the transistor responds, okay, drain current changes according to the change in the gate voltage. So, therefore, it is biased into the saturation region and this R1, R2 helps this transistor to maintain the voltage, gate voltage VGS here, this one DC voltage. Okay. I am showing here AC voltage, actual input which is applied at the gate. Let us say it is gate here, drain and source. Now, one more important thing, this RS, okay, is provided with a source bypass capacitor. So, this is the source resistor and we have one capacitor which provide a bypass to the AC from this. Therefore, this is the amplifier, common source MOSFET amplifier with bypass, with source bypass resistor, with source bypass capacitor. So, it is capacitor, source bypass capacitor. So, there are 3 capacitors, input coupling capacitor and this is output coupling capacitor, and we want to take output across this resistor which is not part of the circuit, but it is called load resistor, okay, and this is also not part of amplifier circuit. So, this is the signal source, this is the signal source, and this RSI is the signal internal resistance of source. RSI is internal resistance of source, signal source. Okay. Practically it has some resistance, we are designating by using RSI, whereas this RS is the source resistance, okay, resistor connected in the external lead of source. Now, what we have to do? We have to develop AC analysis circuit for this, okay. Now, what is the concept here? See, try to understand how voltage is amplified here. Now, this input voltage is applied across this voltage divider network R1, R2 and internal resistance of this transistor, okay. They make a voltage divider network here, and the drop across this network is the actual input to be amplified. Now, let us first of all I will show you what is the input VGS we are getting from this source, okay. Now, let us draw this first, or else we can do first we will develop the small AC equivalent circuit of this, okay. So, draw AC equivalent circuit for the circuit. The first step in drawing the AC equivalent circuit is ground all DC sources present in the circuit, and second point is what we have to do? We have to short circuit all capacitors, short circuit or short all capacitors in AC analysis, AC equivalent circuit. Why to short circuit all capacitors? I will show you. Capacitive reactance Xc is equal to minus J by omega C, which is equal to minus J by 2 pi Fc, okay. F is what? Frequency of input audio signal applied here, and C is the capacitance value. Now, see what happens when F is increased, as it is amplifier circuit and we have to change the frequency. So, this is the composite signal, consists of so many frequencies, and when this frequency increases the capacitive reactance decreases, okay. We can understand the mathematical equation, and because of that at high frequencies this capacitor acts as the short circuit, okay. Therefore, we have to short all capacitors while showing this one, okay. Now, I am going to modify the same circuit. See, I am performing the first step, okay. First step is perform ground all DC sources. I have grounded VDD to ground, okay. Now, short circuit all capacitors. I am going to modify this one, okay. All capacitors are going to be short circuited, and this capacitor also acts as a short circuit, and this is also going to be short. Now, for the remaining things, okay. Now, see, point to remember, okay, is this one, this RS, okay. The effect of RS going to vanish because of this capacitor. The AC current will pass through this, okay, and there won't be any voltage drop across RS, okay. IS into RS will be 0 because the effect of RS is negligible here. So, therefore, the heading is with bypass capacitor, okay. Source bypass capacitor plays an important role determining the magnitude of output voltage, okay. We are going to see that case also. Now, see, I am going to redraw the circuit. So, now what we will do? We will connect this point to the ground, okay. You hold this terminal of this resistor and connect to ground. So, this will be on output side because it is drain, so part of output node, and this is the gate, okay. This is part of input node. So, this resistor, this end will come to this ground. So, I am going to draw this. So, already we have this RSI, okay, signal internal resistance of source, signal source, and we have signal source Vs, and now this R1 will be here, R1, okay. Already this point is at gate, and this another point, okay. This terminal of the R1 is connected to ground. Again we have one more, already we have R2 here, R2 is connected to gate and ground. So, it is gate here, we have gate. Now, see this. Now, from this point we have the gate of transistor, see gate. Now, so this will be without RS, source is directly connected to ground, see, and this drain. Now, see how many resistors are there to the drain. So, this one point and this another point goes to ground. So, keeping this one point as it is, and we are drawing this RD, we are connecting here. Now, what is one more resistor is present here, that is RL, capacitor is shorted here, and RL one point is a drain, okay, this is drain, and we have this RL here. So, it is the RL, fine, and this is the V0, okay. We are not taking VDS, but we are taking simplicity, we are using V0 notation to show the output voltage. Now, where is the VGS? VGS is here. So, this VGS is the input swing, okay, at the gate, and this to be amplified, okay. In terms of V0 we will get the output voltage. Now, what is the concept of amplification here? See, now this is the source voltage. So, source voltage goes through R1, R2 and this complete input resistance of this. So, here we have Ri. So, this input voltage, okay, the complete Vs is not going to be amplified, but there will be some drop, okay. So, we have to develop voltage equation for that, how much voltage is dropped here, what are the factors that causes the voltage drop, okay. Actually, Vs should be equal to Vgs, the whole thing we are getting from the source should be applied to the gate and it should be amplified, but it does not happen, okay. So, this voltage, okay, so this voltage swing, okay, it is given by in terms of resistors and voltages. We can write equation for VGS, and this swing in the voltage will produce a current ID here. So, here it will produce a current ID, okay. Do not write ID here, okay. So, it is the load current is opposite to this one, okay. So, this ID we are showing with a negative indication, okay. So, it is the reverse, it is flowing from drain to source, okay. We have to show this in small signal model of this transistor, fine. Now, this current, okay, multiplied by the total resistance present here, okay, including finite output resistance of this transistor, okay, it will produce a voltage drop, okay, and that voltage is equal to output voltage, okay. So, that voltage plus the drop of voltage here, okay, this VGS. So, the ratio of these two things will give us the voltage gain, okay, and so many parameters are responsible for this, okay. We are going to write equation for that. Now, I am going to write what is VGS here, okay. After that, we are replacing transistor by its small signal model. Now, see how to get value of VGS first. Now, we have source here, okay. So, I am going to simplify this diagram. So, we have source Vs, okay, plus minus, and it is internal resistance of source, and here we have Ri. So, this one is Ri. From where this we got Ri? So, it is R1 parallel to R2. So, Ri is equal to R1 parallel to R2, okay. The combination of this, so it is the resistance looking, okay, from this side it is the input, total input resistance of the circuit. So, it is Ri. So, across this we have VGS, actual input to be amplified, see. So, here it is VGS, okay, and how much it is? So, VGS is equal to, if you apply voltage divider rule, you will get the source. So, it is Vs multiplied by across which we are getting the voltage drop, value of resistors, resistor is Ri, and addition of these two resistors. So, it is RSI plus Ri is the voltage, actual input voltage at the gate of transistor, and it is going to be amplified. Now, from this we will get one thing, okay. So, we can write here. So, what is Vs? We will get equation for Vs from this. So, it is VGS into RSI plus Ri divided by, so it is Ri. Okay. Now see, Vs should be equal to Vgs. Vs should be equal to Vgs, or we can say Vgs should be equal to Vs. Okay. Total source voltage should be applied at the voltage. Okay. That is the ideal case. Now, practically when we have resistors in the circuit, there will be voltage drop here. See, Vs is not equal to Vgs, or Vgs is not equal to Vs. Okay. Why? Because we have resistor values. If Rsi equal to 0 and Ri equal to 0, okay, no input resistance, then at that case only, then and then this Vgs will be equal to Vs, otherwise no. Okay. And this is called ideal case of amplifier. Okay. And we should not keep Ri equal to 0. Okay. The requirement of design of amplifier is that Ri should be infinite and R naught should be as low as we can maintain it. Okay. So, this is the equation for VGS. Now, we are going to replace this diagram. I am going to erase this voltage divider equation. We have developed equation, you write somewhere, we can relate this. We have to draw, we have to replace this thing by a small signal model. Okay. We have to replace this by small signal model of transistor we have developed in the beginning. Now, see, we have RSI, source Vs, and this one resistor. I am drawing a compact circuit R1, R2, and from this we have gate. So, it is VGS and current source. So, it is the current source here, and this current source is Gm times VGS, and here we have what are the things remaining? RD. Okay. Sorry, not RD. So, it is the R naught, finite output resistance of MOS transistor. So, this thing represents the small signal model. This portion is the small signal model for NMOS transistor. We have replaced transistor symbol by using small signal model. Okay. So, this is the ID, I can show here ID small d, and here we have external resistor RL, RD, as well as the RL load resistor parallel to this one. Now, I am going to erase this circuit. Now, we can write equations. We have written the input voltage equation. Okay. What we have? We have equation. So, it is VGS, or we can say Vs is equal to VGS into Ri divided by Ri plus Rs. Okay. So, what we had equation? We had equation VGS is equal to Vs into Ri. So, we got VGS into Rs plus Ri, sorry. So, it is VGS Ri plus RSI, and we have Ri here. Okay. So, this is our equation for Vs. Now, we can write V naught. Okay. So, it is the output resistance here including the load resistor R naught. We will write equation for R naught later. Now, what we have? We have to write the voltage drop here. So, what is the voltage drop here? So, it is the current into total resistance. First of all, what is the total resistance here? R naught. R naught is small r naught parallel to RD parallel to RL. So, this is the total output resistance. Okay. So, this resistance into this current is the output voltage. So, V naught is written as, so it is V naught is equal to, so it is minus ID into R naught. See, simple we can remember R naught. We can substitute value of ID. What is ID? According to this small signal model, it is Gm times VGS. So, it is minus Gm times VGS into R naught, we are substituting this equation, R naught parallel to RD parallel to RL. So, it is the value of output voltage. Okay. Are you getting how the voltage at the input and what is the voltage at the output? Okay. So, these are the values of resistors, okay, that decide the output voltage. Okay. So, designing of amplifier depends upon the external resistors connected with transistor. Now, what is the gain? Voltage gain. If A is the voltage gain, so it is output voltage divided by input voltage. So, this will become, so it is what is V naught equation? So, it is minus Gm VGS. So, R naught parallel to RD parallel to RL. So, divided by equation of VI, equation of Vs, sorry. So, it is Vs here. We are considering source resistor as well, because of that Vs is important term here. Okay, we can use Vi also, but we have taken the source resistance also. So, we will get Vs, okay, substitute equation for Vs, Vgs into Ri plus R. We have this equation now, minus Gm Vgs R naught parallel to Rd parallel to RL and Vgs Ri plus Rsi divided by Ri. So, this Ri will be up, Vgs is cancelled. So, it is minus Gm R naught parallel to Rd parallel to RL divided by Ri plus Rsi multiplied by Ri. Okay. See here. Now, what happens if source resistance is ideal? So, this is the equation. So, practically we have this gain, okay, which shows that what is the role of resistor? RD, load resistor, input resistance. Okay. The internal resistance of source, signal source, and it is the Ri input resistance. Okay. So, this is the gain of common source amplifier with all these values. Now, we can develop the approximate equation. Okay. If we have ideal signal source RSI equal to 0, okay, then what will happen? We will get A is equal to, so it is minus Gm R naught parallel to Rd parallel to RL, and this Ri gets cancelled. Okay. I am going to write one more step. So, it is Ri if RSI equal to 0, and this is the equation. Now, say suppose R naught is very high, finite output resistance is very high. So, say it is approximately infinity. Again we can write approximate equation, and RL equal to 0 without load resistor, what will be the approximate gain? So, this A will be minus Gm, so it is Rd. So, this is the approximate equation of voltage gain of common source amplifier with source bypass capacitor. Okay. Now, one more question, what this negative sign indicate? Okay. This negative sign here indicates that input and output, okay, the input to be amplified and amplified output. If this is the input Vs, okay, and amplified output, amplified version of this, okay, now they are out of phase. See this. So, this is the output V naught and they are out of phase. When we use one transistor exhibit, okay, 180-degree phase shift between input and output. Okay. Remember, this is most important point. Now, see, we have approximate equation for gain with source bypass capacitor. Now, we have to develop equation of voltage gain when we do not connect the bypass capacitor across RS. I have drawn circuit diagram of common source MOSFET amplifier without bypass capacitor. Okay. So, I should write here without source bypass capacitor. We will come to know what is the importance of capacitor in the circuit. Okay. In previous case, the capacitor bypass AC signal flowing through source through capacitor because capacitor act as a short circuit. Okay. This is the discussion we have done already. Now, I am going to write the small signal model directly for the whole circuit, okay, AC equivalent circuit as well as by using the small signal model of MOSFET. So, what is the difference here? We have this RSI and this is the source, signal source, and we have the circuit already we have developed in the first section, and it is the R2 and we have gate here. Now, here we have some change, little change. So, it is the source, current source as it is, and it is GM times VGS, and we have R naught here, small R naught, which represent the finite output resistance of MOSFET, and we have drain here. Okay. So, this is for MOSFET, small signal model of MOSFET. Now, here we do not have bypass capacitor, this one. So, there will be voltage drop across this. What will be voltage drop across this? So, it is RS and IS will flow through this, because source electron move from source to drain. We have studied in the working of NMOS transistor, we have source here and we have drain region, and this is oxide layer and this is metal layer. Okay. And it is plus gate, and this is source and this is drain. Once again I am telling for understanding. This source, from source electron move from this channel. Okay. Electrons are moving and the current is flowing from this drain to source. Say this, drain to source, because it is at higher potential and it is at lower potential. The current is flowing from drain to source. Now, see, IS approximately equal to ID. So, IS source current approximately equal to ID. So, this is the relation, because it is flowing from same channel. Now, see, any drop in the source will cause drop in the drain. So, here the drop across this IS RS. So, this is the IS into RS. This is the voltage drop, and definitely it is going to affect the output voltage here. Now, see how it is. So, this is the RS without bypass capacitor, RS. Okay. And what is the drop here? So, it is ID. It is ID into RS. What is ID? GM VGS into RS is the voltage drop across this. Now, see, this is the circuit we have. So, it is at ground and we have this RD. Now, we can show here. So, these are the parallel combination of RD as well as the parallel combination of RD and RL. So, this is at ground. If you connect here, that is also correct, and this point is open. Now, see here, you can connect this point, no problem, fine. Now, we have this one. What is the voltage here? Actual gate source voltage, swing. And what is the voltage drop here? So, this is common to input and output. Therefore, we should write the voltage drop across this. So, this is the, so it is GM VGS. What is GM VGS? GM VGS is the current. So, this is the current we are showing here, current source. So, this is the current, and what is the resistor value? RS. So, GM VGS into RS is the voltage drop across source resistor. If we do not use capacitor to bypass current through it, and it is going to cause the voltage drop across it, and this is the kind of a negative feedback. So, what is negative feedback? Due to negative feedback, output voltage decreases, and we are going to prove it. We are going to write equation for that. So, if you write VI here now, what is VS? What is VSC? VS is equal to total voltage drop, VGS plus GM VGS plus RS. So, I am going to write equation for that. So, what is VS? So, VS is total VS is GM VGS plus VGS plus, so this voltage plus this voltage. So, this voltage plus this voltage. So, it is total VS is equal to VGS plus GM VGS into RS. So voltage plus voltage drop, okay, both are voltages. So what will, if I take VGS common, it will be VGS 1 plus GM RS. So this is the value of source voltage, okay. So it is the KVL. Applied source voltage is equal to voltage drop plus voltage drop, total voltage drop, okay. So by using KVL we got this equation. So this is like equation number 1, and already we have equation for output voltage drop, okay. The parallel combination of all these things, we have V naught. What is V naught? So it is minus GM VGS, this is the current, and the R naught parallel to RD parallel to RL, okay. So without considering the internal resistance of the source of the signal, we have this, okay. Now we can find the gain equation for that. So it is V naught divided by Vs. So we will get, so it is minus GM VGS R naught parallel to RD parallel to RL divided by, so it is minus GM, sorry, Vs is VGS into 1 plus GM RS, okay. So VGS get cancelled, and what we have equation is the voltage gain. So it is minus GM VGS R naught parallel to RD parallel to RL divided by 1 plus GM RS. So this equation, okay, is different from earlier one. So we had only this part, okay, and here what is the additional? Additional is the denominator, okay. So the gain is going to decrease. What is the factor? 1 plus GM RS, okay. So by this factor the gain without bypass capacitor decreases, okay. So this was the analysis by using source bypass capacitor and without bypass capacitor.